Lesson 4.5 is titled Solve Quadratics by Finding Square Roots. In this lesson, what we'll do is we'll take a quadratic function in standard form and kind of move things around and solve without having to factor. The first thing we want to do is clarify the difference between a symbol with x squared and a symbol that has the square root in it. If you have this first term, like the first part of a quadratic function, we would say that that's x being squared. So like x squared plus 5x plus 6, for example. The opposite of a square root is have that symbol in front, and you would read that the square root of x. Anytime you solve an equation, you always want to do the opposite operation. The opposite of squaring x is taking the square root. What's going to be helpful to us in simplifying is knowing our perfect square factors. We've used these already in factoring, but they're also useful in simplifying square roots. When you look for perfect square factors, these are the perfect square factors from 1 to 20. Pause the video and write them down as quick reference, and we'll use these to simplify the examples on the right-hand side. Once you've written them all out, press play, and then we'll use them. The directions are to simplify each expression, and they all have square roots in them. The first one is the square root of 100. Over on the left, that's one of our perfect square factors already. 100 is known as a perfect square. And that means the answer is going to be a whole number, and you won't have a square root in it. The square root of 100 equals 10, because 10 times 10 equals 100. So you're doing the opposite operation. The next one, though, we're not quite as lucky. We have the square root of 24. Now, 25 is one of our factors, but 25 doesn't go into 24. So your goal is to see if any of those other factors go into 24 evenly. 24 can be broken down into 1 times 24, 2 times 12, 4 times 6, and 3 times 8. 4 and 6 would give you the biggest perfect square factor. So if we break apart 24 into 4 times 6, and you write them both inside the square root of 4 times the square root of 6 would equal the square root of 24. And that's helpful for us in simplifying because the square root of 4 is one of our perfect square factors. That equals 2. The square root of 6, however, stays on the inside. That means 2 square root 6 is our simplified form for the square root of 24. Our next example is quite a bit bigger, the square root of 363. Let's see. 1 goes into it, but that's not going to help us simplify. 2 doesn't go into 363. 3 goes into 363 121 times. And look at that, everybody. That's on our list. So 3 goes into 363 121 times. That means if I take the square root of 3 times the square root of 121, I would get the square root of 363. The 121 is our perfect square. So that's going to go first. You always write the perfect squared answer first. The square root of 121 is 11. But the square root of 3 is stuck on the inside. The simplified form, then, of the square root of 363 is 11 times the square root of 3. All right, one more in this row. Over on the right, we have the square root of 19. 19 only has factors of 1 and 19. And 1 wouldn't change the value for your answer, and unfortunately, 19 isn't a perfect square. What that would indicate is that 19 is already simplified. In our next example, we have the square root of 12 times the square root of 6. Notice it's a product, kind of like how we wrote the ones up above. Unfortunately, neither of those are perfect squares. When this situation happens, what you want to do is actually multiply them together. 12 times 6 is 72. And now kind of treat it just like we did up above. Let's see if any of our perfect squares go into 72. Well, 1 does, but 1 times 72 doesn't really do us a whole lot of good. The next perfect square is 4. 4 goes in 18 times, so that's a choice. The next one's 9. Guess what? 9 goes into 72 8 times. So we have lots of choices so far. 16 doesn't go into 72 evenly. Neither does 25, but check this out, everybody. 36 goes into 72 twice, and 36 would then be our biggest perfect square. When simplifying, that's your goal. You want to try to find the biggest perfect square factor. If I take square root of 36 times square root of 2, the square root of 36 is a perfect square. That equals 6. The square root of 2 stays on the inside, and that's simplifying that product. Our last example in this section has numbers on the outside and the inside. When something like this occurs, we just multiply kind of corresponding locations for each part of the problem. The 3 can be multiplied easily with the 7 to equal 21. That's on the outside of the square root symbol. The inside, though, has a 5 and an 8. Neither of those are perfect squares, so let's start off simply by multiplying them together. 5 times 8 is 40. Now the 21 on the outside is going to stay as is for now, but the square root of 40 we can try to simplify with our perfect square factors. 1 times 40 would work, but neither one of those would simplify very well for us. 4 goes into 40 10 times, and I think that's it for our perfect square list, either 1 in 40 or 4 in 10. The 4 is a perfect square, so if we do the square root of 4 times the square root of 10, the square root of 4 would come out as a 2. And the square root of 10 stays on the inside. But don't forget about that 21 out in front. If the 21 was already out in front and we take out that perfect square factor of 2, we multiply the two answers together. 21 times 2 would give us 42. And then the square root of 10, stays on the inside. There's a reason we have to work with practicing how to simplify square roots when we solve quadratics like the ones down below. Solving by extracting square roots. This is another method that we can use to solve if maybe we don't have all the parts for standard form, or maybe if factoring doesn't work for us. This is also useful when that bx term is missing. So sometimes we've had it missing before and we were able to factor, but it doesn't always factor when it's in standard form. So if the bx term is missing, this is what we do. The first thing you want to do is get whatever term is being squared by itself. Then we think about doing that opposite operation. We're actually going to take the square root of each side. Here's the key on this. When we take the square root, we have two types of answers, a plus and a minus answer. This is going to be critical when we simplify. Speaking of simplifying, the last step will always be to use our perfect square factors to simplify the inside of the square root if possible. That's a lot of information. Make sure you get these steps written out, and then we'll put them to the test over on the right. Here we go. It says solve each equation. Seems simple enough, but it also says be sure to state both possible solutions, that's the plus and minus rule, in exact simplified form. So that's where we'll use our perfect square factors. We're not going to use our calculators to get decimal approximations. So here's what this looks like. We have x squared equals 289. Notice it's not in standard form. We have an x squared, but we have a number on the right. We didn't set it equal to 0. But when you have just x squared and the bx term is missing, we don't have to necessarily set it equal to 0. If we can get x squared by itself, the next step was to take the square root of each side. So just physically writing that square root symbol. Remember up above we said these were opposite operations, so the square root cancels out the squared for the x squared term, leaving you with just x. But we always have two solutions for x, or up to two solutions. This is where that plus and minus comes in. We'll have some symmetry with the square root of 289. It can be positive or negative. Now, if we look at our list, that it's 289 is actually one of the numbers that's on the list. It's a perfect square. So if it's a perfect square, that means the square root symbol will go away altogether, which is kind of nice. What's crazy about this function is that the perfect square root of 289 is 17. That means your x-intercepts are at positive 17 and negative 17. So you can write it out in this order with just that plus minus symbol, or you can split it up into two parts. Either way, it doesn't matter. And wow, that would be pretty crazy to graph. Let's try the next one. Here's an example where we have 2x squared plus minus 512 equals 0. So this is in standard form, but it's missing the bx term. We do not have to try to factor it if we recognize we could move the 512 over by adding. So the first step is to try to isolate your x squared term. That gives us 2x squared on the left equals 512 on the right. But to truly get x squared by itself, we need to get rid of the coefficient of 2. Let's divide that out and see what happens. I've isolated x squared on one side, and on the other side, 512 divided by 2 is 256. Then the next step is to take the square root of each side, and that cancels out the squared term, and that gives you x by itself. Remembering to keep the plus or minus in our answer, here's another situation where our answer is a perfect square factor already. The square root of 256 is a perfect square, and it's plus or minus 16. Again, another pretty big quadratic function if we had to go to positive 16 and negative 16 to plot our x-intercepts. They won't always be perfect squares, so let's look at the examples down below that require us to simplify. In example C, we have 1/2 times x squared minus 8 equals 16. It's kind of in standard form, but we've got 16 on the right, and we're missing that bx term. This is an excellent opportunity to try to isolate the x squared term. We'll first move the 8 over by adding it. And we have 1/2 x squared on the left, and 16 plus 8 is 24 on the right. Now to get rid of that 1/2, we've talked about this for off and on throughout the semester, but it's been a while. Fastest way to get rid of a fraction is to multiply by the reciprocal. And that cancels out the 2's on that left-hand side, giving us x squared, which is what we wanted. On the right, 24 times 2 over 1 is 48. The next step is to take the square root of each side, and remember that cancels out the squared term and gives us just x. Always recognizing that plus or minus to give us our two solutions. And unfortunately, 48 isn't a perfect square. It's super close to 49, but we're not adding to get factors, we have to multiply. So let's take a look at how we could break 48 down to find our end result. I know 1 is a perfect square, 1 times 48, but that won't help us. The next perfect square is 4, and 4 times 12 gives us 48, but let's keep going. 9 doesn't go into 48 evenly, but 16 will, 16 times 3. And that's going to be our biggest perfect square factor. Like we did up above, let's simply put the square root over both of those and recognize that the square root of 16 is the perfect square. That comes out as the 4. The square root of 3 stays stuck on the inside. So this would be where the x-intercepts are at plus or minus 4 square root 3. That's the exact answer. If, however, we were graphing, we would have to plug it into our calculator to get a decimal x-intercept approximation. Okay, we have one more scenario where this is going to be helpful. For example D, we have x minus 3 in parentheses squared equals 72. If this entire term is being squared, we can get rid of the squared right away by taking the square root of each side. It cancels out the squared, but we are stuck with that x minus 3. That doesn't change. And on the right, what we also have to remember is that the plus or minus will go out in front of that 72. And let's see if we can figure out how to simplify the square root of 72. If you recall from up above, we actually simplified the square root of 72 to be 36 times 2 as our biggest perfect square factor. So if we take the square root of each part, we still have x minus 3 on the left, and we still have our plus or minus, but that 36 is going to come out as a perfect square, 6, and then the square root of 2 is stuck on the inside. So that's the answer that we had up above on this page. Unfortunately, we don't totally have x by itself yet, so we still have to do that. To get x by itself, it's simple enough to add 3. But where we put 3 on the right is going to be significant for our final answer. The 3 on the right goes out in front of the plus or minus. To get that symmetry, we would start at 3, and then we could either add or subtract the 6 square root 2 approximation. So that looks really different, and unfortunately, make sure to write this down, does not equal 9 square root 2 or negative 3 square root 2. We can't combine the first two parts because they're not like terms with that square root. So the answer that we have on the first part of the problem, that I'm just kind of erasing that squiggle, this answer right here is the valid answer. And that's 4.5. We'll do a little bit of practice in class tomorrow.